think we are good to get started. So a couple of housekeeping notes. Today we've got the Balancer team here to do an overview of their code walkthrough for what's in scope as part of their V3 competition that's happening at the moment. If anyone has any questions throughout, feel free to drop them in the chat and I will interrupt politely when it best suits. And then the final note is I'll be uploading this recording to the Cantina YouTube channel shortly afterwards as well. So I'll hand it over to Daniel and Wani to do a brief intro and then get stuck in.
Awesome. Thanks for the intro. Well, my name is Juani. I'm the lead of the smart contracts team in Balancer. And we've been developing Balancer V3 for about a year now, and we are very close to launch. We've been going through the audits these past few weeks. And yeah, today I would like to introduce you to the code. I will try to go from general to more detailed. I will take that approach throughout this call. There's a lot going on in Balancer V3. There are a lot of new things that we introduce in the design. And I will try to cover the most important ones. Please feel free to ask questions. And yeah, if we have some time at the end, I will also go through the code. But yeah, for now, I'll just explain what's most important. So let's get started. This will be a bit intense. So the agenda for today is essentially first an overview of what V3 is, then a stop over the architecture and some highlights, like a very high level description of how V3 works, what are their main components, and so on and so forth. Then a deeper dive, where I will dive into some details and specifics of things that are also interesting about V3 and its design. And finally, some time for questions and answers. So what is Balancer V3? It's many things. It's a decentralized exchange that allows fungible liquidity positions, the same as Balancer V2 or Uniswap V2, which means that, for example, when you add liquidity to a pool, you will get an ERC20 token in return, representing your liquidity position. It has a single vault, same as, for example, Balancer V2 or Uni V4, which means that's the contract that will hold all the liquidity. And it's also designed to hold yield-bearing tokens and yield-bearing liquidity in general. It's also a DeFi platform. It's not only a DEX, but it's built with the focus on developer experience so that others, third parties, can build their own pool. Also pools that have like custom behaviors, custom invariants. We'll briefly touch what an invariant is, but also hooks, which means that you can take an existing pool and add complementary code that modifies its behavior. And everything is optimized and designed from the ground up so that building on top of Balancer is as easy as it can be. That means that some of the complexity has been pushed to the base layer, and we will cover how we did that. But that's more or less the idea of the design as a whole. And finally, Balancer V3 is not only the contracts, but also all the integrations that come on top, the SDK to interact with the contracts, the front end, and so on and so forth. There's a lot of work that has been done for Balancer V3 to actually work end to end and for the liquidity to be usable. But for today, the most important part of this talk is going to be centered about the smart contracts, which is what matters in terms of the competition. So let's go through the architecture. The main component of Balancer V3 is, of course, the vault. It's a contract that holds all the funds. And its main purpose is essentially isolating both pool and buffer balances. We'll cover what a pool and a buffer balance is very soon. Essentially by providing internal accounting for these abstractions. So essentially, if you're familiar with any DEX, you might know that you essentially add liquidity to a pool, and from there you can trade tokens that are inside that pool. And there are different designs out there. In Balancer V2, it's also the same. You have a vault that holds all the contracts, and then you can plug pools. The pools essentially only do the math and provide some pricing mechanism for the tokens in the pool. but the tokens themselves are held by the vault, not by the pool. In UniV2, for example, tokens are held by each pool, so the pool both holds the tokens and provides the pricing mechanism. But on Balance V2, Balance V3, and for example also UniV4, there is a single contract that holds all the funds, and then you can plug pools to it to provide the pricing mechanism, which is a nice abstraction. And in our case, it's very important because it allows us to plug in different pool types and build different and interesting abstractions on top of a base layer. Buffers are also like an internal primitive of the vault, and they essentially are pools that trade one-to-one. We'll cover that in more detail throughout this talk. So as I just said, essentially the vault, okay, it has pools, but it also has to provide a primitive so that users can interact with those pools. For example, adding liquidity, removing liquidity, swapping tokens through a pool, and so on and so forth. We'll cover what those primitives are, but essentially, yeah, I mean, if you have a contract that holds the funds, it also needs an interface to interact with those funds and to do interesting things with those funds. As I said, the point of Balance V3 is to build on top. So this is a base layer. It also provides some functionality to the pools that are built on top, and we will also cover that through the talk. And another important aspect is that it controls the BPT supply. We'll call BPT the Balancer Pool token, which is essentially the token that represents the liquidity positions in Balancer V3. So again, you add liquidity to a pool, you get BPT in return, an LP token, which is an ERC20 token, and the vault is able to control the supply of all the liquidity positions that live in Balancer V3. And finally, well, it also collects protocol fees every time the user swaps, or if there's a pool with yield-bearing tokens. The vault takes a cut both for the LPs and also for the protocol and or pool creators. So that's more or less what the main component is about. If you want to go for the highest price, of course, this is the most important piece, and that's where you should look first. So how does the vault work? We are using this cache till pattern. It's very similar to what UniV4 has done, but also very similar to Balancer V2, what we did essentially with batch swaps. And it essentially means that you do a set of operations and you only pay at the end for them. So for example, if you swap like many tokens one after the other, you only need to send the token that you owe, and then you receive the token that the vault owes you after all that transaction. So to do that, the workflow usually looks something like this. You first unlock the vault, then you operate, you do whatever you want to do. That operation will probably create credits and debts in the vault. The vault will essentially track whatever the user owes the vault and whatever the vault owes the user. Then the user has to settle all those debts, essentially paying what it's owed and then getting the funds out of the vault for corresponding to the credits. And finally, locking the vault. And if everything was paid properly, we can continue. If not, the vault will revert. So again, this is more or less the global pattern. And as you might be already imagining, if you need to first unlock the vault, and then operate, and then settle, that's not something that you can do with the vault directly as things are now. So it's not that as a user you can just call the vault and do all of this at once. You will need some sort of contract that interacts and performs all these steps for you. Because otherwise it's like, okay, I call a function, the transaction finishes. So if I only unlock, I'm not doing anything. If I only operate, I couldn't unlock first. So as you might imagine, you need a contract that interacts with the vault. It's not that EOAs can interact with the vault directly. In that context, what does operate even mean? So, well, I said that the vault has primitives. So essentially for pools, you can register and initialize pools, meaning that you can say, okay, this is a pool. These are the tokens of the pool. Please take it into account and like reserve the space to essentially like account for the balances. Initialize is the first time that you add liquidity to it. And from there on, it's like one step that only happens once. And from there on, you can add more liquidity, swap between the tokens in the pool, and remove liquidity. Those are the basic pool primitives. We also have buffer primitives, and buffers are a special kind of pool that trades one-to-one. Again, I will cover that later, but essentially the primitives are very similar. You need to register a buffer, but you also have initialize, add, remove, and swap for buffers. Finally, all these operations are transient in the sense that, for example, when you add liquidity, it's not that the vault, essentially adding liquidity means that you are going to send tokens to the vault in exchange for LP tokens. And when you call add liquidity, it's not that the vault will pull the tokens from you. There's no transfer from in the vault, which means that the vault will only register like, okay, if you are adding liquidity, you're owing the vault a certain amount of tokens. The vault will give you LP tokens in return, but you need to pay for those tokens later on, at some point before the transaction finishes. And that's what transient means in this context. For those that are familiar with UniB4 or Balancer V2, that's more or less what happened with patch swaps in Balancer V2 or what happens in UniB4 where you also need to pay before the end of the transaction. So given all that I've said, this is more or less what the overall architecture looks like. I said that you cannot interact with the vault directly, so we will call the contract that interacts with the vault the router. Balancer developed a bunch of routers that can do basic things, are more or less complex things, like there are like a spectrum of things that can be done with the routers. But there's nothing special about the router. I mean, anyone can write their own router. And again, as long as it uses the vault primitives properly and it settles properly, things will just work. It's not that the router has anything special at all. In fact, Balancer's router can also be upgraded in the sense that it's not that the contract is upgradable itself, but we can just stop using a version of the router and just push another one and start using a new one, and that will just work. The contract that is immutable and cannot change at all is the vault, of course, because it's the one that holds the funds. So changing the router doesn't mean that you can rag the users in any way because the liquidity is always protected by the vault. The router only allows you to interact in a different way with the vault. So again, how does the workflow look like, more or less? So the user, as I said, always interacts with the router first. So the router will also expose the functionality in a user-friendly manner to the user. So the router will have functions to swap, to add liquidity, to remove liquidity, or to interact with the buffers, for example. And the router is the one that calls the vault. As I said, the first step to start interacting with the vault is always unlock. So you call a function to unlock the vault. And from there onwards, the vault starts tracking all the operations that happen that needs to be paid before the end. And then the vault calls the router back. At that point, the router can do whatever it wants. Like the logic there is completely arbitrary. So you can do a swap, you can add liquidity, you can remove liquidity in the vault, or you can do any combination of those. You can like maybe do a series of swaps, or do a swap and then go to another protocol, do something else and come back and pay. So there's no restriction there really. The logic that the router has is completely arbitrary. Of course, the basic routers have what you need to do basic operations, so you don't need to care about that. But again, it's super flexible and anyone can write their own custom router. Once the operation is sent to the vault will usually rely on pools to do the pricing mechanism. So for example, if you want to swap, the pool will say, okay, if I send you 10 token A, how many tokens B will you give me? And that's more or less the interaction that happens between the vault and the pool. In principle, the pool can be just math, like I give you this amount of tokens, how many tokens of the other kind will you give me? Or if I add these amounts of tokens, how much BPT should I mint? Or things like that. It's like there's no, it's pretty basic what the pools do, and it's pretty isolated how they should work. Once the pools return with the results, the vault will account for that, saying, okay, this is what I need to change the pool balances for, this is what I owe the user, and so on and so forth. Maybe also, depending if it's an add or remove liquidity operation, I need to modify the BPT accounting, so modify the LP positions. Maybe I need to mint BPT shares if you're adding liquidity, or burn BPT shares if you are removing liquidity. And all of that is returned to the router. With that result, the router can choose to settle, saying like, okay, now this is the result I got. Now I need to pay the vault and take out the funds that the vault owes me. And it does that essentially by using permit 2 in this case. So you don't even need to do approvals neither to the vault or to the router directly, but to permit 2. And essentially the router sends tokens to the vault to pay the debts and takes tokens out of the vault with another primitive back to the user. If the settlement goes well, meaning that everything is paid for and there's no outstanding debits or credits after that, then you can just finish and the vault will try to lock itself back. The vault will check that effectively all of this happened and that there are no outstanding debts or credits. And after that, the transaction finishes. If something went wrong, for example, I swap 10 tokens A for token B, but I forget to pay, or I try not to pay, the vault will say, hey, you owe me money, and it will revert and won't let you continue. So that's more or less how this works. This is all powered at the core by transient storage. And it's a great tool because essentially it allows the vault to register everything that's happening within the transaction in a cost-effective manner. Like before transient storage, you would, like if you wanted to do this, you either need to do it in memory, which is what we did in Balancer V2, but it has some limitations, or using regular storage, which is very expensive in terms of gas. But with transient storage, you can essentially record what's happening inside the transaction itself, just for the transaction, which is exactly what you need, and the cost is much lower. Yeah. If you don't have any questions, I will just continue. So this is a summary of the trades that I've described so far. So again, settlement happens at the end, meaning that you always pay for the tokens and receive the tokens from the vault at the end. This also means that this design is very easy to query. And by query, I mean like doing a static call that tells you how much tokens you would get, for example, with a swap or with any operation. And this means that you can essentially like do a dry run of the operation itself, but without settling in a static context. And that's the query. And with that, you ensure that in most cases, like the query will be exactly the same as you would get in the actual operation because you're executing the exact same code, except that you're not settling because it's a static context. You don't need to actually move the funds. But the math that you're doing, like throughout all the code, like with all the interactions between the router, the vault, and the pools, are the same in the actual operation as they are in the query. Also, the fact that there's a router means that the vault doesn't need to expose very complex primitives. I mean, yeah, the vault is fairly complex, but it doesn't need to, for example, expose how to swap more than one token or a series of transactions all at once. The vault just needs to expose like swap, add, remove, and primitives for the wrappers, and then the router can combine them in any way it wants. And that means that the vault, I mean, yeah, it is complex, but it is relatively simple in that regard. It doesn't have like a super complex API. Also, super complex APIs are incompatible fundamentally with immutable contracts because at some point you might need to extend them. So all of that now is the responsibility of the router. And in the future, if we need a more complex router or a router that does something different, we can just like deploy another one. And that's a very interesting aspect of this design. And again, the vault holds the tokens, reverts and settles transactions. So if the router tries to trick the vault and take funds without paying, the vault will revert. The vault also needs to keep pool balances isolated, and this is very important. For those that you are familiar with Balancer V2, that's also the case. You essentially have the pool balances, and if one pool goes bust, because you cannot prevent registering a pool that gives away tokens, and that's fine, and it's contemplated in the design as long as it doesn't affect other pools. So first key, if you want to find a critical bug, you should try to look at that. Essentially, no matter what the pool is, you shouldn't be able to drain all the vault's reserves. At the most, if the pool is wrong, you should be able to only drain that pool that is wrong. But you shouldn't be able to drain the balances of other pools that also are stored in the vault. So that's the most important property of the vault. Of course, that's accomplished by reverting unsettled transactions. But yeah, if you want to find a crit, that's the way. You need to find a way, like a bug that breaks that balance isolation. And another important thing is that, as I said, Balancer is meant to build on top. So the vault takes also a lot of common responsibilities out of the pools, which makes building pools pretty easy. That pushes some complexity into the vault, and you will see when you go into the code. But we thought it was a fair trade-off because we really wanted to provide a good developer experience in Balancer v3. Again, as I've been saying, the router is upgradable. You can just ditch the current router, deploy a new one, and start using it. So that makes the external and user-facing API much more rich and easier to use. And another small thing that I haven't mentioned yet is that this design supports reentrancy. I will cover this when I dive into the details. But this means that, for example, you can trigger operations within operations. Essentially, each operation has a sort of life cycle. For example, if you try to swap, there's a before swap hook, a main swap hook, and an after swap hook. And you can trigger other operations, for example, before the swap. So you can do a swap before the swap, or add liquidity before the swap, or whatever you want, essentially, before the swap. That allows for very interesting and fairly complex patterns to happen. But yeah, this is all contemplated as part of the design. So I've been saying that the vault is a base layer and takes away some responsibilities from the pools, and it makes building pools easier. So briefly, what are those? The first one is token scaling. Pools will usually deal with tokens with different decimals. Also, there can be tokens that have rate providers that are essentially yield bearing, where the rate grows over time, which represents the yield they're accruing to that token. And essentially, the pool shouldn't care about all those details. Like, pools should care mostly about, okay, what's the balance? Let's just do the math, apply the pricing mechanism, and that's it. And for that to happen, sometimes you need to take into account what the decimals are, because otherwise you're kind of comparing apples with bananas. So that's more or less what the vault does. It scales all the token to 18 decimals and applying also the rates if they have a rate, and they send that as a balance to the pools, so that the pools can only do math. They don't need to deal with all that token scaling and unscaling that is kind of difficult to get right. We also have unbalanced add and remove liquidity kinds, which means that, for example, to add liquidity, you need to add liquidity proportional. So for example, if you have a 4 token pool, if you only have add liquidity proportional, you need to get all the 4 tokens to provide liquidity to that pool. But rather, we use a mechanism where you can add liquidity with, for example, 1 token or 2 tokens in any amounts that you want. And between the pool and the vault, they will solve how to do that properly. This is somewhat complex, but a very interesting UX feature, because it allows, like, I mean, maybe for 2 token pools, it's not that important because you can just like add liquidity proportional. It's not that hard. If you only have 1 token, you just do a swap and then you add liquidity proportional. It is some friction to the user, but it's not that bad. But now imagine that if you have like a 4 or up to an 8 token pool, if you need to add liquidity proportional and you only have 1, you need to do like n-1 swaps to get all the other tokens to add liquidity. So that's super inconvenient. So all of that is solved in Balancer v3 in a novel way that, yeah, it's pretty well packaged, let's say. I'll dive into that later on. Protocol fees, yeah, I mean, that's the tax, let's say, that both Balancer and pool creators, pool builders that build on Balancer also have a native mechanism to earn fees on chain, and all of that is handled by the vault. Post window is essentially a mechanism, an emergency mechanism to halt everything that happens, like you cannot swap, you cannot add, you cannot remove. So in case there is a problem with a pool or with the whole vault, governance can step in and pause everything to halt the operation. There's a pause window, so after some amount of time, you cannot use this feature anymore. But the idea is that, for example, for the first 4 years, you can pause both pools or vault. And of course, you need a sort of escape hatch so that the protocol is completely non-custodial, because otherwise you can just pause the pool or the vaults and then no one can exit, which would be a huge problem. So recovery mode is essentially the alternative that gets enabled whenever someone pauses a pool or the vault. Recovery mode can be enabled, and that allows a escape hatch for people to exit their positions if things go wrong. So that's more or less like all of these things are packed into the vault. Again, this adds certain complexity, but again, if you are building a pool on Balancer v3, you get all of these for free, and you don't need to care about that. And that's the trade-off that we took in this design. Any questions so far? I mean, this is gonna be like the most, maybe difficult part of the talk. So far, it's been like very high level, and now I would like to get into like the details. So yeah, let's dive in. So how do you build a pool on Balancer, and what does that even mean? Like, what is even a pool type? So I will take two very basic examples, like weighted pool and stable pool. Those exist in Balancer v2, and the invariants. The Balancer weighted invariant is essentially an extension of Uni v2, like where x times y equals k, but extend that to more than 2 tokens. You can also have, for example, the stable invariant, and that's essentially just a pricing mechanism that says, okay, if you add liquidity to a pool with a certain invariant, this is what the price curve will be. So given these balances and given the invariant, you can compute swaps, for example, like, okay, at this price point, I'll put 100 tokens A, how many tokens B will you give me? And that depends on the current pool balances and its invariant. So for example, the stable invariant has a much more flat curve than a weighted pool invariant. And that's very useful, for example, for assets that should be worth more or less the same, such as, for example, USDC and USDT. Weighted invariants are better for example, ETH and USDC, which are not correlated. But on top of that, you can keep innovating and push your own invariant. There are others, in fact, that already are live in Balancer v2, and we hope to bring them in Balancer v3. I'm using these two as an examples because they are just like pretty popular and rather simple. But the idea is that we can formalize how to build a pool by providing these 3 core methods. So essentially, a pool is a contract that implements onSwap, compute invariant, and compute balance. Truth is that if you're familiar with AMM designs, like in fact, the swap function is defined by the invariant. I mean, once the invariant is defined, essentially an invariant is something that doesn't change when you swap in a perfect world, right? Where there's no fees or anything like that. It means like, okay, you have to stick to that curve before and after the swap. So once the invariant is defined, the pricing mechanism and the swap function is defined. But what happens is that in many cases, you can provide a swap function that is gas efficient and doesn't need to compute the invariant in some cases. That's the case, for example, with weighted pools. You need to compute the whole invariant to compute a weighted pool swap. In some others, it does depend on invariant, but that depends on the pools. It's just like, it's pool dependent in that case. So again, building a pool is essentially implementing these 3 functions. OnSwap is, again, I give you some amount of tokens. How much will you give me? You have swap kinds. It can be exact in or exact out. It depends on the balances, and it depends on the invariant of the pool. Compute invariant is just like formalizing this mechanism. I mean, any pool that operates under fungible liquidity should have some sort of invariant, and you need a way to compute that. And then compute balance is a sort of reverse invariant, which is like, okay, given these balances and given an invariant ratio, which If you add liquidity, it will be greater than 1. If you remove liquidity, it will be smaller than 1. Okay, given balances and invariant ratio, what is the balance of a given token to respect that new invariant ratio? So that's more or less what you use to compute and balance, add and remove. In the most minimal form, the only thing that you need to actually implement a pool is on swap. But if you want to provide unbalanced liquidity functionality, you also need compute invariant and compute balance. All of this is in the code, so you can already take a look at what compute invariant and compute balance looks for stable swap and for weighted pools. In the case of compute invariant, it's literally like figuring out those two formulas. So in the case of weighted pools, it's just like the product of the balances power to the weights, and that's it. That's literally compute invariant. And compute balance has some quirks, but yeah, it's when you see the code, it's gonna make sense to you. So this is just like a very brief summary of what building a pool looks like. Then, of course, like looking at the code completes the picture. Some more notes about this. As I said, like the invariant defines the pricing curve. Essentially, once you define the invariant, that's what defines what the on-swap should be. Then the LP position must be fungible, which means that if you multiply all the pool balances by k, for example, by 2, the invariant will also grow by 2. And that's an important property and ensures that the liquidity position is fungible, because it means that, okay, I have a certain amount of liquidity. Then if I double that, the invariant is a sort of measure of the value in the pool, so it should also double. If it doesn't double, and if, for example, it goes 4x, it means that the liquidity that you're adding is worth more than the liquidity that was in the pool, which doesn't make any sense. So for the liquidity position to be fungible, you always have to respect this property. Again, if you multiply the balances by a certain constant, then the invariant will also grow by that constant. And that's a very important principle to have in mind when building pools. And as I said, all of this allows unbalanced liquidity kinds. By unbalanced liquidity kinds, I actually mean something like this. So for example, if you want to add liquidity with a single token or with many tokens with the amounts that you, like arbitrary amounts that you want, that is all covered. If you want to exit the pool with just one token instead of all the tokens, it can also be done. And yeah, more or less the same. Like for remove liquidity, you only have single token exact in and exact out. So you can specify how much BPT to burn, for example, that's exact in, and you will calculate how many tokens you receive. Or you can also say, I want to receive 10 tokens, how much BPT do I need to burn for that to happen? So that's the UX improvement that is like very important for mostly for multi-token pools that have more than 2 tokens. And all of that is solved, again, by providing those 3 methods that I described before. If you want to see how all of this works, maybe the hint is to take a look at baseball math, and that's where all of this is solved. Moving forward from liquidity operations, maybe we can touch base on an operation lifecycle and what hooks are. So we can take a swap, for example, and if we have a swap, when you call the vault will essentially have an on before swap hook, an on swap hook, and an on after hook. The on swap hook is essentially the one that provides the pricing mechanism, and that's solved by the pool. And again, it's like I gave you 10 tokens A, how many tokens B will you give me? That's what on swap solves. And then on before and on after are 2 callbacks that can be implemented by a separate contract that doesn't need to be the pool, and that's the hook. So for example, you can plug a hook to a pool and do an action before a swap and after a swap, or both, like whatever you want actually. This also applies to add liquidity and remove liquidity, so you can combine them as you would like. And also on before and on after can also trigger another operation. So for example, you trigger a swap into a pool that has a before swap hook. The before swap hook will get called, and that before swap hook can do whatever it wants, including adding liquidity to another pool or to the same pool, or like anything really. It's not limited by anything. The only one that cannot trigger another operation is the onSwap itself, for example. So the function that gets called to the pool and is called onSwap. And you cannot add liquidity inside onSwap because that's the one that modifies the balances, and that's the critical part that is protected by non-reentrancy guards. But that's more or less what the lifecycle looks like. And again, the main onSwap or onAdd or onRemove is mandatory. OnBefore and OnAfter are optional, and you can choose to configure the pools that way when you register them in the vault. What else is there? With security in mind, there are a few things that have been done at the vault level. And this includes rounding. Rounding should always be in favor of the vault, which means if you are trying to compute an amount out that you will give to the user, you're going to try to round it down as much as possible. And if you're computing an amount in that the user owes the vault, you'll try to round the result up as much as you want. Under regular circumstances, rounding is basically not important because it will be just like a few way. And if tokens have like a lot of decimals, it's like users won't even notice that there's some rounding going on. But this is a protection in case mostly for like pools that might be sensitive to what happens in the very last way of the operation. And also for pools that have very low liquidity. That's where the rounding impacts the most. So if you're a hacker trying to break the thing, you will probably try to go that way. And rounding is essentially a protection for that not to be exploitable. All of that is mostly handled at the vault, and the pools also have to do their part. Essentially, when you're computing a swap, the pools need to round in the right direction. And there are some hints that should be documented already on how to implement a pool properly for the math to be sound. When I say guardrails, I say like, okay, the system should work even without the guardrails, but we know that many exploits happen when you are around like very specific conditions. Like we've seen a lot of exploits where the first steps, like the preparation steps, are like, okay, let's put a pool in a very low liquidity level so that we can exploit a rounding error, where a rounding error is like more impactful than under normal conditions. Or let's try to swap like one way for two way, or let's try to put one way in and get two way out and then try to amplify that. So it's always like trying to push things to the extremes. And those are really not valid use cases. I mean, if you want to swap one way of token A for two way of token B, like get out of my vault, please. Like we won't allow that. So one guardrail is like there's a minimum trade amount. If you try to swap or add liquidity in very low amounts, the vault will revert. It won't let you. There's also a minimum pool liquidity. When you initialize a pool, a small portion of the shares is burnt forever and they cannot be accessed anymore. And this means that if you are the first LP, you won't be able to get exactly what you put in when you initialize. In most cases, it's going to be negligible. It's not that the user, like the first LP of a pool, is even going to care about the value that is lost forever because it's really dust. But it does impose like a minimum liquidity condition for the pools. And that also helps keep the math safe and sound. And another thing is swap fee boundaries. Essentially, if you have a pool that you are not very sure about, or if the math is not sound, for example, at very high swap fee percentages or very low swap fee percentages, pool developers can set those as constants so that you cannot go above or below those fee limits. And again, this is important because we are plugging in different pool types that have different math constraints, and it's not easy to make those safe and sound for any swap fee percentage. So with this, you can limit how the pool should be used, all in the spirit of allowing good cases and valid use cases to move forward properly, but disallowing potential exploits that may happen. These are the most important guardrails. There might be a few more here and there, but the idea is that it's all about layers. It's like with these guardrails, we're trying to prevent the pre-steps that usually happen when an exploit happens. Like usually it needs a preparation step where you do something very weird that is not a valid use case. So we're trying to just prevent those from happening. Even in the case there is a rounding error, some of these guardrails should catch the hacker in the middle of an exploit. So even if you can find a rounding error, perhaps it won't be exploitable because of the minimum trade amount or the minimum pool liquidity and so on and so forth. Let's briefly talk about buffers. I also said that besides the pool, the vault has buffers, and they're essentially like native linear pools that are sort of embedded in the vault. Linear pools are essentially pools that always trade one-to-one. So you put one token in, you get one token out. And while that doesn't seem very interesting, you can think of it, for example, with tokens that have their yield-bearing version. So for example, you deposit USDC to Aave and you get a USDC. There's a wrapper for that is not rebasing token, which is called wrapped A USDC. And you can essentially create a buffer between USDC and wrapped A USDC. And this allows you to trade USDC for wrapped A USDC. Essentially, it's a sort of swap interface that you can add to interact with Aave. So again, there's a lending protocol. There's a token that is yield-bearing. And this provides some native mechanism to sort of swap between the vanilla USDC and the yield-bearing version wrapped A USDC. Of course, the rate is taken into account, so wrapped A USDC is worth more over time. So as time passes, like that one-to-one means that one USDC will be equivalent to less and less wrapped A USDC over time, and that's how it preserves the value, of course. But the point is that this is a sort of like mini pool functionality in the sense that you can also add liquidity, you can swap. It has more or less the same primitives as the pools, but it's simpler and it's just aiming for cases like this one, particularly ERC-4626 wrappers. So what you can do is deposit liquidity to these wrappers and use that liquidity for cheap trades. So instead of interacting with Aave, like going to like change USDC for wrapped USDC, go into Aave and doing everything that is behind, you can just like do a small swap using buffer balances to swap between vanilla USDC and the yield-bearing wrapped AUSDC. So that's more or less the idea behind buffers. Besides that, the buffers can eventually go very one-sided. So when you, for example, if you want to wrap USDC for wrap and get wrapped AUSDC in exchange, if there's not enough liquidity, the vault will go to Aave or any underlying lending protocol and rebalance the buffer so that the trade can go through. So this allows us to build booster pools. For example, you can have a 100% booster pool that has, for example, wrapped A USDC and wrapped A DAI. So if you deposit liquidity there, is basically the same as depositing to Aave, but you will also earn swap fees in the process. So the point is that this should be strictly a bit better than depositing to Aave because we will also get swap fees, and it's a sort of swap interface between the Aave assets. But the problem is that for this liquidity to be used, I mean, it's very hard for people to actually hold wrapped AUSDC or wrapped ADAI. People just like either go to Aave and deposit and hold the rebasing token, or they only have the vanilla token like USDC and DAI and want to swap between the two. So if you put buffers to the side, like if you have a buffer between USDC and wrapped AUSDC and a buffer between DAI and wrapped ADAI, you can construct a swap that hops through the two buffers and the booster pool. So that allows you to do for first wrap USDC for wrapped AUSDC, then swap that wrapped AUSDC for wrapped DAI, and finally unwrap that wrapped DAI for DAI. And all of that can happen. There's a router that does all of that for you by using both buffers and pools. So that's more or less the goal and why buffers are there. Essentially, again, whenever you want to do this hop of USDC for wrapped USDC, if the buffer has liquidity, that step is going to be very cheap in terms of gas because you don't need to go to Aave to do all of that. So that's more or less the rationale behind buffers and booster pools. Let's go with a practical example, and this is something that you can do nowadays. Imagine that you have pool A that has DAI, USDC, or USDT, or actually the wrapped versions, wrapped DAI, wrapped AUSDC, wrapped AUSDT. Then you have a second pool, which is the BPT of pool A paired against wrapped stake ETH. Like that's a weighted pool. And then you have a pool C that is wrapped stake ETH against VAL. You can actually construct a swap path that is vanilla DAI for VAL. And first, you will essentially need to add liquidity to pool A, then swap pool A, the token of pool A for wrapped stake ETH in pool B, and finally swap wrapped stake ETH for VAL in pool C. And you can do all of this in a single transaction and querying what the result will be in advance by using the right router and by combining the right vault primitives in the process. So that's more or less what you can achieve with all of these primitives and constructs. And finally, one note about the vault. When you go into the code, you will see it. The vault is actually a huge contract, so it has to be distributed throughout 3 contracts because of bytecode size constraints. So the vault is actually the vault plus the vault extension plus the vault admin. And we are using a proxy pattern here. There is a common layer that all of the 3 contracts inherit. So the vault is vault common, the vault extension is vault common, the vault admin is also vault common. And what happens here is that essentially the vault is also a proxy. So if you call a function that is not in the vault will go to its fallback method and delegate that call to the vault extension. So for example, if you call a function that is not in the vault, it will go to the fallback and it will be delegate called to the vault extension. The vault extension does the same. If it's a function that it doesn't find, it will delegate call it to the vault admin. So for example, if you want to pause a pool, that's a function that actually exists in the vault admin, which is the second code extension of the vault. So the vault will delegate call the vault extension, and the vault extension will delegate call the vault admin. And only then the request will be processed. A small note about this pattern is that since we are using proxies and delegate calls, all the storage is actually in the vault contract. The vault extension and the admin are just code extensions, and they don't hold any relevant storage whatsoever. Like all the state, all the token accounting, all that is relevant is stored in the storage of the vault. The other contracts just share the same storage layout. So actually, if you delegate call something to the vault extension and you write the state within a delegate call in the vault extension, you're actually going to be writing the storage of the vault. And that's how everything kind of makes sense. And again, what you need to know at a very high level is that the vault is a proxy. It's actually, the functionality is actually distributed throughout 3 contracts, vault, vault extension, and vault admin. But all of the storage is actually in the vault. It lives in the vault, and the extension and the admin don't have any relevant storage. So that's more or less it for now. We have some time for questions and answers. If there's nothing, I can briefly go through the code and show you like the entry points. These are 2 very good resources. Well, of course, the repo. I will start with the README. You can check the instructions to build and run the tests in the README there. And also, of course, there's the docs page that it also has very good high-level descriptions of everything that's happening. I would highly recommend you to go that way as well. Thank you for listening, and yeah, let me know if you have any questions.
Thank you so much. Yeah, as Wani mentioned, if you've got questions, drop them in the chat and I can put them forward now. I can see someone typing.
Sure, of course. I'll share it after the meeting ends.
Perfect. I can get that link included in the competition page as well.
Again, this is a very high-level explanation. Feel free to reference it, but also the docs is a very good reference to get started.
Cool. If no one else has any other questions, then obviously the team is also contactable via Cantina and Discord as well. So if you think of any questions, feel free to drop them in there. But really appreciate both of your time today. This was awesome.
Thank you. If you want, I can use 5 more minutes to take a very quick dive into the code and where things are more or less.
Yeah, that would be awesome.
Okay, can you see the... Perfect. All right, so this is a Yarn monorepo, so it has a lot of packages in here. Everything is inside the root/package. The names are very descriptive, and most of the meat that you will need to look into is inside the vault package, as you might imagine. So here are all the main contracts. Again, if you go to the vault, that's the contract. But yeah, there are also others. The routers are also here. If you want to check what the regular workflow of an operation is, you should start with the router because that's the entry point. So for example, swap single. If you go, for example, to a swap function, you will see that all the entry points look something like this. You have a function that has a lot of arguments, but it's very user-friendly because, okay, I'm swapping a single token. What's the token in? What's the token out? What is the exact in? What's the mean amount out? So it's like super easy to read. And all the entry points look something like this. As I said, the first thing that you do is actually unlock the vault. And if you see, like, the argument of all of this is actually a callback, an encoded callback. It's like, okay, unlock the vault and call me back using all of this. Like, call me back to the swap single token hook with all of these arguments. If I go to the vault, you will see that unlock is actually just, okay, call me back with whatever you send me, but it does have this transient modifier, and this is the key to ensure that everything is paid for. Again, what it does is like say, okay, let's try to unlock first. If it's unlocked, I don't do anything, but if it's locked, I unlock the vault. Then I do whatever I need to do. Here's where the callback will actually happen. And after the callback happens, I try to lock again. If I see that something was not paid, I will revert. If everything was paid, I can just continue. That's the very basic workflow that I just described is all summarized in this transient modifier. So this is the most important piece. Again, then what happens, like all the meat of the code is actually here. And this is actually, okay, call me back to whatever you told me to call me back. In this case, we said that it was the router. And in this case, it's the swap single token hook. Again, the router, essentially what it does is call this swap hook, which essentially is calling the swap primitive. It needs to adapt the parameters a bit to comply with the swap function. And then this gives you the router the result. Okay, this is the amount in, this is the amount out. I need to take the amount in. That's for, this is essentially like sending tokens to the vault. And send token out is essentially receiving the tokens from the vault. Another important detail is that the vault doesn't handle any native ETH. All of that is handled by the router. So if in this case we are handling ETH, we probably need to wrap and return leftovers if needed. And that's it. Like, that's a simple swap. At the router level, that's very simple. So as you can imagine, most of the actual code is inside the vault. So I won't be able to go into details, but yeah, I mean, the router eventually calls this, and this is what solves the result. It's like, okay, it's essentially, here's the request. This is what I want to swap. I want to swap this token for this other token at this pool. what's the amount in and what's the amount out is the answer to that question. And here's where everything happens. You essentially need to load the balances, you need to scale the balances, you need to condition more or less the parameters and the internal data so that then eventually you can call the pool. Here's where that happens. And with the result that you get from the pool, you then perform all the accounting that is needed, both in terms of credits and debits and also pool balances. And that's more or less what it looks like. Again, I cannot go deeper than this because of time constraints, but you get the idea. Again, the router unlocks the vault calls back the router performs the operation with the vault and settles. And then the operation in the vault is where most of the things actually happen. That being said, I'm running out of time, so good luck. Yeah, good luck. Looking forward to see all your submissions, and please feel free to ask questions throughout the competition if needed. Again, thanks for listening.
Thank you so
good
much.
luck again.
That was awesome. Have a good day, everyone.